Word on this computer. I'm going to go ahead and get started because it's quite possible that today is going to be our last lecture and we will not meet Monday because I have jury duty on Monday. And it's possible that they don't need me. That's what's happened in the past, right? They send me a message the night before, hey, you're not needed to come in. So I'll keep you posted about Monday. However, yes, I will do virtual office hours tomorrow, and I plan on sending an announcement tonight out to hopefully hold some extra meeting time tonight. I have time after class as well, I believe. I have a meeting with other professors at 1 o'clock, but otherwise I am fairly free. We'll see how I'm doing though. Okay, encryption, one exception. I see that audio. Yeah, that makes sense. Okay. So we're going to go ahead and go through and again, we're going to do what we kept doing and go over the review for the final exam. Okay. What we're going to do first is that I wrote this study guide for you. And we can find it here. We can find it on, let me go ahead and pull it up on Firefox, GitHub, A.B. Rosen. And we can find it under Classroom and Destruct. This is a fairly old thing I wrote, but the nice thing about data structures is that you don't really need change like what the study guide is. And here is the link to it. You'll be able to download it through a download button. It's the same thing I'm pulling up on my screen. I'm going to drop it in chat for everybody. But otherwise, you can, click on the GitHub link that I have on Canvas and find it that way. But this is just a list of the topics that you want to make sure you study, okay? So just kind of a list of topics to make sure, okay, do I know these things? Okay, first off, make sure you know your big O notation, right? Another one is make sure with recursion, that's especially related to trees. Make sure you know how to do recursion especially as it relates to trees. So if there's going to be a tree question, you're almost certainly going to, the way you're going to solve it is almost certainly going to be recursive, right? And if you need to, right, don't be afraid to write extra functions, right, to make a public and private function, right, to make the accessor at the top end and then the second one to help you do what you need to do, a second recursive method. For sorting algorithms, yes, I go over a lot in the videos. That's fine. So here, what we do is that we have, is I want you to know insertion sort, quick sort, and how the partition operation works. So it's not enough to know, oh, quick sort, you have a pivot, everything that's shorter goes to the left, everything that's greater than goes to the right. I want to know how the computer actually does that in place. And then knowing merge sort. These basically just know like how it works, what the runtimes are, and why those runtimes are what they are. We'll go over that today with some of the more theoretical questions I'll be covering. Huffman encoding, you don't need to worry about. And that's we've been emailing about the exam over the past couple days. Huffman encoding is not something you need to worry about. Lists. Know the difference between array lists and linked lists, right? Remember what your big O times are for each of those. Your stacks, your queues, right? Make sure then when you're reading that, I don't think we have any questions like this, but in general, you want to make sure, are you reading a binary tree versus binary search tree? And remember, all your algorithms that you deal with trees are either find based, meaning they're gonna be in log n. What does that mean? You're trying to find something in a tree. You're going left, right, left, right, left, right, left, right until you hit something. So it's a log n algorithm. Or it's a traversal based, meaning that you need to recursively travel to every single thing in the tree, right? And that's pre-order, post-order, or in order. Okay. Sometimes it doesn't matter. Sometimes it's very specific about what we want. Heap, you definitely want to know. It's always a complete tree. And you want to know how to turn an array into heap in O of n time. Specifically, that's what we call the heapify algorithm, right? And that's where you start at the bottom and progressively turn all the items, start from the back of the array and turn item and basically say, okay, from the back forward, let's make sure that this tree turns into a heap properly. I go over a lot of examples. I go over a few examples of how to do that. Your textbook does, but it's called the heapify algorithm. Make sure you know that. Hash tables are used to build sets of maps, right? We use .hashcode to generate a unique key. Mod table length to find the place to put it in. These two things combined are called the hash function. And just know basically, okay, we've got a collision. How do I resolve it? We learned two ways in class, chaining, and then also which says basically every slot in the array, underlying array, is actually a linked list. So we just kind of make it so we form it, so we chain them together. Another way that a lot of students find is better is called buckets, called bucketing. Yes, you're allowed a cheat sheet, I believe. Actually, I believe so. I will send an email, but I believe you're allowed a cheat sheet. I think that's fine. We're still working out the specifics of the final exam, but I think that's fine. Such as where we're going to hold it. So I'm going to send an email out with all the information about the final exam, okay? Okay, but I believe we are going, because I'm still not sure where it's held, if we're holding it in our normal classroom, or we're not holding it in lab, okay? I know that much, but are we holding it in the normal classroom, or are we holding it in a large classroom that's been reserved for everybody? Okay. So I'll send that email out. If you have questions, about that, and you're worried about that, and you don't know by the end of the week, feel free to reach out to me via Discord or email. Right. So the other way to know, which is open addressing, probe for an empty slot, grab the first one we find. So we always look for the next open spot. What's the next one? Either we look for the literal next one, or we hop over like we saw. For graphs, right? Representations, adjacency list, adjacency matrix, right? One of those is, so we can represent a graph in one of those two forms. And then you want to know breadth first search, depth first search, and Dijkstra's algorithms. Those are the three algorithms. These find you paths in unweighted graphs. Shortest paths, they find you just paths in general in unweighted graphs, as well as weighted ones, but they're mainly for just like exploring the graph. They're algorithms to build off in general. Dijkstra's has a specific function given a weighted graph, right? Find the shortest path from a starting node to all other nodes. I did send the link earlier. It's up in the chat. I'll send it again. Okay. Copy link, paste link. There you go. All right. Some of these are dead, but two of them are not. One of the links used to go to to an older version of the Harvard final I showed you yesterday. So here are some other questions. And there was only one question on the other dead link that I'll go over. All right, so final exam in algorithms and data structures. So this is kind of straddles, this class, from what I can tell, kind of straddles our data structures class and our algorithms and data structures class. So don't feel scared if like this kind of this is notation that you would care about for the next class. Like, what's the difference between O, omega, and theta? Instead, there's some other questions that I really like here, like this one. Consider insertion sort and merge sort. For each algorithm, so this is an algorithm that if I wasn't showing it here, I'd totally cheat and put it on the exam, right? Insertion sort and merge sort. For each algorithm, what will be the worst case asymptotic upper bound? So in other words, what's the big O runtime on each of the following algorithms, right? And you're like, well, that's simple. O of n squared, n log n. But then it says, if additionally you know that the input is sorted, it's been reversely sorted, and the input is just simply the same item repeated over and over and over again. Okay? So let's take a look at insertion sort. Insertion sort, right? I like this question because this kind of shows what insertion sort is really good at. Murphy, no. Sorry, cat. Insertion sort is really good at dealing with items that are lists that are partially sorted or already sorted, right? What it does is that if we have a bunch of unsorted items, a bunch of sorted items, it will go through, okay, this is the right place, this is the right place, this is the right place, this is in the right place. Oh, this one's not in the right place, so we'll move that one. Okay. On the other hand, if we get something that is already sorted, right, it actually turns out to be a really nice situation. 1, 2, 3. Insertion sort will simply go, oh, that's already sorted, that's already sorted, that's already sorted, that's already sorted. Don't need to push this one down, right? So I don't need to push this, don't need to push this, don't need to push this down, don't need to push this down, don't need to push this down. We're done. It takes, so in a sorted list, it takes O of n time because we got to find because we look at each one once. Okay. If it's reversely sorted, on the other hand, that's the worst case scenario for insertion sort, because every item has to be moved the maximum amount of times. Let's take a look. 5, 4, 3, 2, 1. Okay, 5 is in the right place. That's fine. Okay. But now we've got 5, but now we're looking at 4. 4 is less than 5, so we need to swap 4 and 5. And now 4 can't be pushed down any further, so we're done. Now we need to look at 3 versus 3 is less than 5, so we swap them. Okay, 3 is less than 4, so we need to swap that. And then 3 doesn't have anything else to compare to, so it's at the front. So we're done with 3. It's inserted into the right place. Then 2, as you can see, would have to compare to 5, 4, and 3 to end up over here. And then 1. And so basically, we're dealing with that 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to n. So it's O of n squared. So the last one was, what if each input is the input is a list containing n copies of the same number? Well, and I'm assuming that means that it's size n. So the list is size n. So that means, what if the list is, instead of 1, 2, 3, 4, 5, it's 5, 5, 5, 5, 5. Well, that's also O of n, because that's technically sorted, right? All the items are the same. Congratulations, it's sorted. Make sense to everybody? Now, insertion sort's even easier. Merge sort is even easier than insertion sort. Why? Because merge sort does not care about these things. Merge sort always runs the same way. It's got to split things up and combine them. Right? And so that always will, so merge sort will take n log n time no matter what the inputs are. It doesn't ever get any better. It doesn't ever get any worse. Make sense? Okay. So let's see. We know that hash tables are very common in practice when you have a lot of insertions, deletions, and search operations. We see it under the assumption of uniform hashing, collision by resolution by chaining, and constant time computable hash function. Insertion and deletion are both constant time plus n over m in the average case. That's just a weird way of saying it. We've also seen that this fact can be reduced over to 1, big O, under the additional assumption. And the answer is that so long as you've got plenty of space, right? As long as you've got plenty of space open, Donald Knuth has that Knuth has that formula saying that lookup time can be related, the expected number of lookups for a hash, for insertion into a hash table or searching for a key, uses a formula where we don't even need to rely off of how many items are in it. Right? Let's go. Now that one wasn't, now this one's though, even better. This is another one of my favorite problems from this exam. This is a good one. Suppose you have a hash table and inserted some elements. When you inspect it, you see that the result looks like the picture below. And being a good student, you realize that it is problematic. What is the problem? Give an example of a hash function that causes this problem. Okay, so let's look at this. So it's doing hash so we can see, because these are linked lists, that we are doing resolution by chaining. Index 0 has 0 and 30. Index 2 has 21, 31, and 1. 4 has 2. 6 has 33 and 63. 10 has 15. 12 has 26 and 6. 16 has 38 and 8. Anybody seeing a pattern here as to what numbers are being grouped together? Not necessarily what slot they're in, but what numbers are being grouped together. Anybody see it? Right? 21, 31, and 1 are all grouped together on index 2. What do these three numbers share? 33 and 63 are all grouped together over here. What do these two numbers share? And 26 and 6. Please, somebody speak up.
They share a final digit.
Yep, they share the final digit. That's exactly right. They all share the final digit, which not exactly ideal, but we're also noticing that, so they share the final digit. And so there's a bunch of empty spaces, right? We have a bunch of chains here, but we also have a bunch of empty spaces. Why? Because of our example hash function that could give rise to this behavior. And what is that? Well, 0, anything ending with 0 goes to 0. Anything ending with 1 goes to 2. Anything ending with 2 goes into 4. And anything ending with 3 is going into 6. So I think we can figure out what the hash function is right just from that. Although, right, the hash function is given some x, the index it's going to go to is the last digit. So how do we get the last digit? We mod by 10. So x mod 10, and I'll be explicit over here. And then we multiply that by 2, right? 1 goes to 2, 2 goes to 4, 3 goes to 6, 5 goes to 10. So that's bad because, wait, these spaces that I'm marking, these odd spaces, will never get used. What would be a better hash function? Pretty much anything else. A better hash function would be one that would make sure we do utilize these spaces, right? There's 20 slots, so utilizing all the spaces would be better. So h of x is equal to x mod 20, which is the number of spaces. That would be really good. I think would be really, that would be better. Okay. Let's see. All right, so let's see. Suppose we have no, we don't need to do that one. 7. I'm being selective here again with the amount of time we have. Suppose that we first insert an element x into a binary search tree that does not already contain x. Okay, so we put an item into a binary search tree and we aren't duplicating any items. Suppose then we immediately delete x from the tree. Will the new tree be identical to the original one? If yes, give the reason in no more than 3 sentences. If no, give a counterexample. Draw pictures if you necessary. If you necessary. Got it. Okay. So I think I will necessary. So binary search tree does not already contain x. So here's our tree. I'm just going to do a triangle for our tree. And then we insert x somewhere into the tree. Now, when we insert an item into the tree, it always ends up on a leaf node. Now, this is one big assumption on my part, which is that we're using the binary search trees that we learned how to do in class, which don't self-balance. If it was going to self-balance, I'll change my answer. That's why this is actually why both yes and no can be correct. So for the yes answer, right, that's the one you'd probably give. if you're taking my class, which is, well, the binary search tree does not contain X. Then it contains X, right? And it's always going to be a leaf node, right? When we insert something, it always becomes a leaf. And then when we delete something from the tree, right? To delete something from the tree, we just simply say the parent node, right? Just simply instead, to delete something, it just simply says that leaf that used to be the parent, sorry, that used to be the child. Yeah, that's now set to null. Right? Deleting, the only times we ever move nodes around in the delete operation is when there are children. Sorry, when the node we're deleting has children. Well, what we've done is we've immediately added X, so it's a leaf node, and then we immediately delete it. There's no time to add any children to it, so we just simply remove that and nothing else has to happen. So the answer is yes there. Counterexample is for this one, for no, is no if the tree is like a AVL or, you know, red black tree or a B tree, any tree that self-balances, which it didn't specify, but I want to cover my bases. Any tree that self-balances, once you insert, if it becomes unbalanced, you may do some rotations that end up changing the structure of the tree. And thus deleting that node means you might have a child that you need to remove now and accommodate for that child. So it would not necessarily be the new tree. The new tree would not necessarily be identical in that case. All right, suppose you have a heap with two values, v1 and v2, such that all values are distinct, right? And I'll assume min heap over here. Let h12 be the value. If you insert v1 value 1, then value 2 into that heap, and then 2 and 1 be if you insert 2 and then 1 into it. Give an example where we have a starting heap, values 1 and 2, and adding these two items in a different order give us two different heaps, right? So suppose we start off with a heap like this, 1, 5, 15. It's a min heap. And we want to add a few items to this, right? So it says, let's give us some different items. Let's go with like adding 2, right? And then 3 first. So if we add 2 first, right, what's this going to do? We add 2 first. That's going to 2 will bubble up. It's lighter, so it will bubble up. 2 and 5. And then we would put 3 over here. Okay. I think I accidentally may have found an answer. Let's go ahead and see. Now let's suppose we start with, again, our heap over here, which was 1, 5, and 15. Now let's look at doing 3 first, then 2. If we do 3 first, 3 swaps with 5. And then 2 swaps with 3. Nope, that's going to give us the same answer. But honestly, that does actually give me an idea of how to do this. 2, 3, 5, 6. And there we go. And I think that's all we need, because if we do 2 first over here, this will bubble up over there. And then 3 will bubble up with this one. And then for the second example, for if we do them in the different order, 3 will swap with 5 and 2 will swap with 15. Make sense? So here is H1. Sorry, here's our H. Here is H1, which would be 1, 5, 15, 1, 2, 3. Sorry. 1, 2, 3, 6, 5, 15. And then the H2 would be 1, 3, 2, 6, 5, 15. Okay. Suppose you have a graph like this one below. The dots signify the parts of the graph that that you don't know how many, but it's not a straight link. Okay, you don't know if there's some amount of paths between the start and the goal. You know that there are many paths from the start to the goal. You also know that these paths tend to be rather long. Suppose you want to implement a program that searches for a path and returns the first one it can find. You do no need for finding the optimal path. Don't need to find the shortest path. Just any path will do. Would you use breadth first search or depth first search to do this? Okay. And I think the answer honestly depends on whether what the interpretation of, suppose you have a graph like the one below. If this is a directed acyclic graph, right, where it has a source, this is a starting point, and a definite endpoint, right? If there's no other endpoints, right? If there's no other endpoints over here, like, you know, not goal, although that looks like I wrote hot goal, right? If there's no other endpoints like that, I mean, you might lose some time with, if there's other endpoints like that, you might lose some time with breadth first search. But the main issue is like, if everything ends up, you know, if all the paths just end up at this location, right? And goal does not have any additional edges coming off of it, right? Going every which way. And then even then, I would go with depth first search over breadth first search. Why? Breadth first search will find you the shortest path because it will explore all the paths first, but it's going to explore, okay, let's look at all the first steps of each of these paths, then all the second steps of each of these paths, as well as all the branches of those second steps, and the third and the fourth and the fifth. So essentially, with a graph that looks exactly like this, you essentially will be exploring every single path until you find the first one that lands into this. And that can take a while, right? Whereas depth first search, you start with a path and it might go however which way, but eventually you might have to back up, but eventually you get to the goal. So I think depth first search would find it quicker. All right, so traversal. So let's go ahead and look at the other one. Okay. Because this one also has Dijkstra's in it. Okay. Go back to that one. So nodes in an integer binary tree can be represented by this, right? Again, they're not using generics. Complete the definition method of breadth first search to perform a breadth first search of a binary tree and print the node values in the order they're reached during. In other words, this is asking us to do level order traversal or breadth first search on a binary search tree, which is really not that hard. And I figure this is a good way to warm up with some programming. I do have a harder programming question in mind to help us with practicing with maps in a bit. And again, I'm just trying to target the big kind of questions that I find to be extremely useful over here. So here is the tree that I have from yesterday. I'm sorry, from the day before. Okay, and let's go ahead and write a public void BFS, right? It wants us to say, just perform a breadth first traversal of a binary tree with root R and print the node values as they're encountered. Now, here's the thing about this. In your solution, you may create other instances of other data structures. And the reason it mentions this is because with tree, this is kind of a trick question. You think trees, oh, that's recursion. But with breadth first search, we don't use recursion. Instead, we're going to use a queue to solve that. Right? And it's going to, now, normally I'd have to have an additional data structure to keep track of everything. But since trees are a special type of graph, and I know they're never going to loop back on themselves, I can get away with just using a queue. Okay, so, and I'll show you what I mean. Node E root. So we'll take in the root of the tree, and we don't even need to do to figure that out. Like tree or subtree, right? It's going to work regardless, but here we go. We're going to do a node E. We're going to use node E current. We've used that a lot. And that's equal to the root, right? We're going to start at that root. Actually, don't even need that. Right? Instead, I'm just going to just go straight there. QE is equal to, sorry, QEQ is equal to new, I think linked list is the way to do that. If you write new Q on the exam, whatever. Even though Q is an interface, I'm not really going to be too upset about that, right? So what we do over here then is, and remember, to pronounce Q, all you have to do is just say the first letter and skip everything else, okay? So what we've got to do over here is we simply say, well, sorry, no, not even that yet. I'm skipping steps. Q dot offer the root. That's the NQ operation in Java. I don't know why it is. Oh, right. It's not a queue of the items. It's a queue of the node of items. There we go. That's perfect now. Wow. The queue is empty. Not. Well, the queue is not empty, right? What are we going to do? We are going to say our current node is equal to Q dot poll, which is the DQ operation in Java. Honestly, I find those terminology a bit silly. It should just be in Q and DQ. All right, so what it wants us to do is we found this and we want to visit it, right? And what we need to do is that we need to Q dot, we simply need to, in breadth first search, we will go to the left child and then to the right child, right? So we just simply offer current dot left Q dot offer. All right, and if we were writing pseudocode, this is just basically it. You just simply travel to the left child, travel to the right child. For each item, travel to left child, enqueue it into the queue, enqueue the left item, enqueue the right item, right? And it will go through and it will visit all of them. The main thing we need to figure out what to do now is when we hit a leaf, what do we do? So we've got two approaches. We need to check for null somewhere. That's what I'm talking about. We need it because right now, once we hit a leaf, once current is a leaf, we'll be adding null. Even if we have only one child, we'll be adding null somewhere. So we need to deal with this in some way, shape, or form. There's two ways to do it. The first is that if we can allow, and it basically just simply says, hey, do you want to add null to the queue or do you want to not add null to the queue? If we're going to allow adding null to the queue, all you do is just simply say, hey, if current is not equal to null, and then we say, only do these things if it's not null. Otherwise, we're just going to kind of skip it. Very easy one-line solution to that problem. The other thing to do is kind of the more logical kind of thing, because it feels icky to put nulls into a queue, in my opinion, which is we just simply make sure if current dot left is not equal to null, right? If it's not, if current dot left is not null, add it. If current dot right is not null, add it. So only add them if they're not null. So those are the two ways to do that. I just simply squished those into one line so that it wouldn't get necessarily too much bigger. Right? And that works in Java because Java doesn't care about white space in the same way that Python cares about white space. Let's continue on. Okay. Oh, this is a good one. Here's an adjacency list of a directed graph where there's no weights. What does this graph look like? Draw the actual graph. Good question. Don't know if we have one of these on our exam this year, but if I was writing, we'd probably have something like this. So we have our nodes A, B, C, and D. Right? If you need to anthropomorphize them for some reason, Alice, Bob, Carl or Carla, and Dan or Donna, right? Alice and Bob are from security. It's always Alice and Bob in security. Alice and Bob are always trying to send a message to each other. Okay. And malicious Mallory is always trying to intercept the message, although sometimes it's malicious Malcolm. Okay. So anyway, A, and then we have a linked list, B, C, D. This means A connects to B, directed edge to B, an edge to C, an edge to D. This one says B connects to A. All right, over here, B, it says connects to A. C says it connects to B, and it connects to D. And this one says D doesn't connect to anything. Now, in theory, we can draw this in a way that none of the edges cross over each other, which is pretty cool. And just here, and because I'm an educator at heart, I just want to point out that when you can draw a graph like this and nothing crosses each other, we have a special word for it. It's a planar graph. Okay, if you have to cross them, then it's not planar. Okay, another way to represent this is an adjacency matrix. So how do we show this off? An adjacency matrix would look like this, right? We have, in fact, I will just simply go over here for that because it's easier for me to type. Adjacency matrix would look like this, right? We would have A, B, so I would have space over here, A, B, C, and D, A, B, C, and D. And not sure why it's so difficult to type. And we'll go with A has no connection to itself, and then B, C, and D it has connections to. B has a connection to A and no other connections. You could put zeros instead of dashes, but zero might imply zero weight. So I often like to write dashes if I'm writing things down. C has no connection to A. It has a connection to B, not to itself, and to C. And to D. And D doesn't have connections, directed edges to anybody. There we go. So that's what that would look like as a adjacency matrix. Now the other reason I do this one is because they do a good Dijkstra's. This test writer, this practice test I think is excellent. I just have one pet peeve with it, which is this over here. This is a great Dijkstra's graph, honestly. This is a great graph for Dijkstra's, but they make one crucial thing I do not like. And I try to make sure that this does not happen on tests. You have weight edges, but then they named each of the nodes using a number, and I find that less than helpful. Why? Because it's easy to confuse, because you're already juggling numbers with the weights. So I want to make sure that the names are easier to see. So instead of giving them names like that, what we're going to do is we are going to draw. We're going to go ahead and do, let's do red. Okay. I wanted the other direction. Okay. A, B, C, D, E, F. If you, and feel free to do that on an exam if you ever see something like that. If there's something like you're like, oh, that's gonna be mentally too messy and I want to organize it different, don't be afraid to do that. Now, now we want to use Dijkstra's algorithm on this graph. Okay. And I'm going to be using the chart. I'm going to be making the chart over here. Right. So we've got, actually, let me go ahead and I'll type out the chart over here. So we've got, so for Dijkstra's, we've got, what we need to do is that basically you have 3 rows. You have the vertex, you have the distance, and you have the predecessor. Okay. So we have A, B, and this is the way your tables always start out, C, D, E, F. Okay. And this is the distance from the start, and this is the predecessor. Okay. So we're going to, so when we tell you to run Dijkstra's, we'll tell you Dijkstra's from vertex 1, which is A, to all the other ones. So, and then simply fill out the chart. Okay, it starts out with basically everything being, the distance to everything being infinity, which I'll put as I. Yes, I know that's the imaginary number, but hey. And then we don't know who the predecessor is for any of these guys. Actually, we do know who the predecessor is, in my opinion. The predecessor is, oh, we can get from A to B from A, and it costs infinite amount of energy to do so. That's, I think, an effectively equal statement. A great way to initialize this. And we can get to A from A with a cost of 0 because we just stay there. Okay. So what we need to do is then we now initialize from A. We say, what are the initial distances from A? So the initial edges are this one over here and this one over here. Right, so we're going to go and we're going to start exploring outwards from A. Okay, oh, that's highlighter. That's not what I needed. I need an eraser. Oh, geez. Let's go ahead and. So let's go ahead and explore outwards from A. Okay, so A has 2 edges connected to it. It has a direct edge to B, which we'll write down as we know we can get from A to B, from A to B for a cost of 2. Okay. And we know we can get from A to C with a cost of 3. And then done, because I don't know how to do a check mark on my computer, sure. Okay. So now what we need to do is we need to find which of these do we know which of these is the cheapest. What do we know to get buy as the cheapest? And then we'll explore from there next. So B is the cheapest with 2. B is still the cheapest with the cost of 2. D is still the cheapest with the cost of, B is still cheapest with the cost of 2 for all these. So we'll say we're going to explore from B now. Okay. B has the following edges. We know we can get from B, okay, to D over here with an additional cost for a total for 3. It's not 3 in total, though. Sorry, it's not just 3. What it is that we know we can get from B to D. So we can get to D by going through B. Now, it costs 2 to get to B in the first place, and then it costs an additional 3 to get to D. So the total cost is that we write down is 5, and we get there going through B. Okay, hopefully that makes sense. Next, let's look at the cost from B to E. Cost to get to E, it costs 5 going through B. Going through B costs us 2. So the answer would be 2 plus 5. And because that is less than infinity, right? 2 plus 5 is 7. 7. Last I checked, and they could have updated math since I last checked, but last I checked, 7 is less than infinity. Right? Technically, that's a nonsense statement, but hey. And so we put that down there, and we say we are getting to E from B. And now B has no more outgoing edges to explore, so we're done. So now we need to find the next one to do. C is the cheapest at 3. C is still the cheapest at 3. C is still the cheapest at 3. C is still the cheapest at 3. Let's explore from C. C is still the cheapest at 3. Yep. Okay, C has only one edge, which is E. Okay. And with E, we're going to be comparing that to 7. So to get to E from C costs 1. To get to C, we look at the table. To get to C, it cost us 3. So 1 plus 3 is equal to 4. 4 is less than 7. So we're going to replace what we wrote because that's a shorter path. So we say instead of getting to E for 7 through B, we're instead going to go through C and end up with a cost of 4. That's the way Dijkstra's algorithm works. We keep updating like that. So C is done because it only had one edge. D, so now we look for the next cheapest node to explore from. D is currently the cheapest with 5. But now we go to the next one. E is actually the cheapest with 4. E is still the cheapest with 4. So we just simply look down our table for that. So we're going to go and say E. Let's look through E. E has a single outgoing edge with a cost of 2. Has an outgoing edge with a cost of 2 to F. So that would be cost 4 to get to E in the first place, plus an additional 2. That's less than infinity. So we're going to go ahead and update that to 6 and say we can get to F through E. Okay, F through E. Now we have 2 more nodes left. We have D and F. Let's explore through D because that has a cost of 5 versus 6. Okay, D has 1 outgoing edge, which has a cost of 4 to F. So we're going to be comparing 4, the cost from D to F, which is 4, plus the cost to get to D. We know that the cost to get to D, the optimal cost to get to D, because it's done. So we know the it's the optimal cost. The cost to get to D is 5. So now we ask ourselves, 4 plus 5, that's 9. How do 9 and 6 compare? 9 is greater than 6. We don't want to take the more expensive path, so we don't update. Now we have 1 node left. It's F. F has no outgoing edges, so we are done. And that's the way Dijkstra's algorithm works. Okay. So the running time of Dijkstra's algorithm is actually kind of interesting. The way I just went over it, And again, the hardest part about Dijkstra's algorithm is learning how to spell it. And again, the animations from Wikipedia for these kind of math related article are pretty good. And the more janky they look, the more old they look. This one's been here since I was in undergrad. The more useful they can be. Worst case performance, V log V. So Dijkstra's original algorithm is O of V squared because we kept checking that table over and over again and didn't do any optimization. Using heaps, using a heap instead, a minimum heap to figure out what the next one to do is, helps keep that runtime down. And that's something you'll learn about, I think, in 3223 if you take that. But basically, there's the original algorithm that Dijkstra came up with versus this. Also, Dijkstra, just as a heads up, like Dijkstra's one of the things Dijkstra was known for was his handwriting. Which is this on the cruelty of really teaching computing science. He had very notable handwriting, just very kind of clear and concise. Some rather popular. So anyway, just a side note. So a lot of his notes are just handwritten stuff. Let's see, where were we? Okay. Sort, sorting. Okay. The two most common divide and conquer algorithms are quicksort and merge sort. In practice, quicksort is often used for sorting data in main storage, that means RAM, rather than merge sort. Give a reason why quicksort is more likely to be preferred sorting algorithm for this application. Okay, so first off, we need to recognize something. What's the worst case scenario for quicksort? It's O of n squared. But in practice, this never happens. It's always the average case, which is n log n, which is equivalent to what merge sort does, right? They're equivalent. So why do we care? Well, because merge sort is, merge sort. Worst case space complexity. Unless you're using with linked lists, unless you're sorting on linked lists and everything is being stored in linked lists, you have to use extra space for your merge sort. Linked lists, it doesn't matter because breaking up and splitting apart and recombining linked lists, that's what they're great at. That's what they're used for. But otherwise, you have to make new subarrays for merge sort and that whole recursive process, and it gets kind of messy. Quicksort, on the other hand, quicksort, we can do that in place, right? Quicksort is an in-place sorting algorithm. And if we look up quicksort, right? We look up quicksort, scroll down, not even going to bother typing it in because we've got all sorts of things over here. Right, here's our list of sorting algorithms. Where is quicksort? Which one does it come out to? Why can't I find it? Weird. Am I just not seeing it because I am feeling dizzy? Control F quick. All right, it talks about quick select there. Oh, there it is, exchange source at the very end. Okay, I was just curious. Quicksort can be done in place. And that space complexity, that's more of the stack being used than anything else, right? It can be done in place, which is pretty cool. Also, notice this, best case performance is we can specialize this, and we could actually get this to run in O of n time on a best case scenario where we're where something good might happen. Just like insertion sort has some niche edge cases where it can run in linear time. But merge sort always is n log n. So so storage reasons, and there you go, right? And we've already adjusted that. In practice, okay, so then part B, quicksort is, right, just we were saying, O of n squared, expecting runtime n log n, right? And what needs to be true about the partition function in order for it to be n log n? That's part one of this. And part two is, in practice, how does it happen? Okay, so in order for the partition function to work, right, you need your partition, so you need your pivot to be over here, and then you need half of the items to be less than P, and half of your items to be greater than P. So you have to choose your pivot, right? I'm sorry, yeah, less than P, and then greater than P. So you have to choose your pivot such that like approximately 50% of the items end up over here, and approximately 50% of the items end up over here. Yeah, and a more inequitable split is okay, but we want as close to 50-50 as possible. Okay. In practice, how do we ensure that this happens? Because if we randomly just simply select the first item as a pivot, it could lead to bad outcomes. A few ways we can do it is that we could instead, we can simply look at the first item. When we're looking at an array or subarray, we can look at the first, middle, and last items and choose one of those as the pivot. Or you could even do that for 5 items, right? But basically, we choose one of those as the pivot instead. We choose an item that's closer to be a middle value. Okay. In order to do that. And let's go ahead and talk about now a problem that was from the other text, from the other one that I wanted to go over. Okay, review, do. Okay, so suppose we have a problem that looks like this, right? You have a text file that looks like that's formatted like this. Username, login, and then session length. So it's a list of usernames, so who logged in and how long they logged in for. Okay. Who logged in, how long was that session, right? Sessions can be multiple, a user could have multiple sessions. Okay, so file might look like this. Alice, 500, Bob, 600, Carl, 700. The units don't matter. We don't really care. It's all made up anyway. Okay, Alice again, another 500, Bob got maybe 1,000 over here, and then Alice logged in again, okay, for 2,000 units, whatever that is. Could be seconds, right? Could be minutes. Don't really care. That's not the point of it. So it could look like this kind of file, right, in this format. And so the question that I want to find out is a function or a method or function that returns for each user their average login length. So the average amount of time they spent logged in. Okay. So I think this is a pretty good test problem, even though it's honestly, the code would actually be a bit long for a test, but I think it's a really good one. Why? Doesn't tell you what data structure to use initially. Okay. We've got a text file. We got to read that text file, and we got to say, okay, so Alice has 3 entries in here, right? The answer in this case, if we didn't see Alice anymore, for Alice, we'd say, oh, Alice was here 500, 500, 200, sorry, 2000. So that's 3,000 units, 3,000. So she's been logged in for 3,000 seconds and she logged in 3 times. So that's an average of 3,000 divided by 3, which so she logged in on average for 1,000. Yep. And so in direct message, somebody said hash map. And yes, we need a hash map. Actually, we don't need a hash map. We need 2 hash maps for this. That's the fun part of this one. Why? Because we're going to be counting 2 separate things. We're going to be counting the total amount of time Alice logged in for, as well as how many times she logged in. Make sense to everybody? So what we'll, and I think we'd even need a third to return. So let's go ahead and do public static hash map. The last answer will be, we're going to return a string, which is the username, and let's go with a double because we'll be dividing. String double, right? And what we'll do is we'll say that and let's keep, and now we need a name. Find average logins, right? And we'll take in, and for this one, I'll say we'll take in a string file name because we need to read the file. And then we will return null for right now so that we can continue programming without any errors, right? Hopefully you've gotten into the habit by now of making sure that when you write a function, you immediately do something to make sure it doesn't have any errors, be it creating an empty data structure or returning null. So what do we do now? Well, first step first is that we are going to read that file. Are we going to read the file? I prefer to do it via scanner. Scanner is equal to new scanner, new file, right? And file name. Now let's call that, let me give this, rather than using file so many times, I'm going to call this file name, right? Because that's what it is. It's the name of the file. It's not actually the file itself. This creates a file object to represent that file. And then scanner lets me read that object. And then it's going to give me a warning saying, hey, you should probably surround this in a try-catch loop. And instead, let's see. Surround with try. Surround with try-catches. Let's see. Yeah. Unhandled exception file not found. Okay. So sure, we can do it. We can surround with a try-catch block. Try. Nah, that's fancy. We're going to do it just a try. And then catch. File not found exception. We will say, and then at that point we will say return. We will just E. Okay, we'll just not worry about it too much. We can also just simply say, or we can be super lazy, which I'm actually going to do, which I think I'm going to do now, just simply so it's less indented and easier to read. But this is going to, I'm just going to simply say, hey, whoever calls that, that's your problem. So we need to scan that, and now we'll read the file. And as we're reading the file, we'll figure out what do we need. So scanner. So while scanner dot has, let's see, yeah, scanner dot, oh, sorry. Scanner dot has next, not has next, but has next line. Well, we can read a line from scanner. String line is equal to scanner dot next line. Make sense? Boom. There we go. And then we've got the parts of the line, which is going to be string parts is equal to line dot split. You've done this in 1051 if you were in my class. I've done this multiple times. line.split. In Java, you have to specify what you're splitting over, and I'm just simply going to say I'm going to split over a space because it says it's going to be split by a space. There we go. And it's not just a string, it's a string array. That's what it splits it up into. Right? And we'll further, and then we're going to just ignore the whole parts of instead we're just going to be explicit about it and say string string username is equal to parts 0, right? That's the first part of that of the line. The first part of the line is the username. The second part is the logins, is the session length. And so let's go with int session is equal to integer dot parse int parts 1. And now convert that into an integer. Okay, so we've got the parts. So what we need to do now is, now that we've read this, we need to do things. We need to keep, for each user, we need to keep a running sum of how long they were logged in for. And we also need to keep a running sum of how many times they logged in. So let's go ahead and create that. So 2 maps of integers. Map of string to integer is equal to, and let's see, this one will be for keeping num logins. Num logins is equal to new hash map. Here, then we're going to go ahead and do a num, and then session length, or we'll call it login or total time. Total times is equal to that. And then finally, let's go ahead and just get it out of the way. Average login, and this is going to be a double instead of an int, right? Because we'll be doing division, and I'll be converting those integers into doubles. Why? Because that's just cleaner for doing averages. And so we want to return the average login. Average logins. Okay, now that we've got this all set up. Okay, so first off, we saw this user. So first off, if username, let's see. So first, let's just simply do the simpler thing, which is counting how many times they've logged in. If username is not a key, then we are going to say we've seen it once. So what am I doing? I'm saying if num logins dot contains key username. And let's go ahead and turn that into a not. So if it does not have the key, and yes, there's simpler ways to do this, but like, or more Java specific ways to do this that's going to suggest. Unwrap if statement. Where to go? That doesn't matter. Okay. But I prefer to do, but I'm going to do it in the more kind of straightforward way. If the number of logins does not, if we haven't seen this user yet, then we've seen him once now. Num logins parts 0 is this over here. Right? Each line has 2. So what we do is we read each line. Each line has each line is a string of username space number. Okay? Username space number. And what split does is that it splits it into 2 parts. And so the part 0 was that first part, the username, and the second part is the number. Yes, part 0 is the name. And then so that I don't have to keep remembering it's part 0, I just simply set it as, I just simply store it in a username. I created an extra variable just so that I can don't have to keep mentally keep track of that. So if we haven't seen this username before, we're going to put that we've seen the username and we've seen it once. Else, what we're going to do is we're going to say int prev logins is equal to num logins dot get the username. So if we haven't seen it before, we've seen him once. Otherwise, we get the number of times we've seen that user. And what we do is that we just simply say, hey, that we're going to update that value. We're going to update that value and say this user logged in the number of previous times he logged in, but one more than that now. Okay, now you might think, okay, now I just basically copy paste this and do the same for and do something very similar for total times, right? To do that running sum. But actually, we can use this because these are going to be using the same keys and they're reading over the same lines. So I don't have to make a separate if-else statement. If I haven't seen it in one, I haven't seen it in the other. So if I haven't seen this user at all, right? I've seen him once, and now let's go ahead and write down how many times. Let's go ahead and say he's logged in. I've seen him once now, and he or she logged in for this amount of time. Total times dot put username and session, how long that session length was. Otherwise, we could do the same thing over here, right? Another 2 lines. I'm going to go ahead and just do what I tell you not to do. And I'm going to do it as 1 line where I'm going to say, hey, update this user's name time to the amount of time that they've logged in previously, get username, plus the amount of time they've logged in now. Right? You see how this is just simply the same as these 2 lines together, essentially. I just kind of did it as 1. Okay. Now, average logins. What's going on over here that it doesn't like? Required type hash map. Ah, okay. Now we need to do the average. Okay. So what we do is we say to calculate the average, let's go ahead and iterate through each again, and we can do it because we know that the keys are the same in both. For string username and you got to use the for each loops for this, for our for these data structures, because order isn't a thing. For each username in let's go with average not average logins, that's the one we're trying to solve. Num logins dot key set. So we're going to go through all the keys. Okay. We'll do, and each key only appears once, so we don't really need to do any if statements or anything like this. It's just a very straightforward but long operation, long text operation. So average logins dot put, and it will be num logins. It's the total time that user logged in dot get username. That's the amount of time that user logged in, and the number of time divided by the number of times they logged in. And that is correct, even though it is giving me an error. The reason it's giving me an error is that I've got a integer divided by integer, which in Java yields an integer, and then I'm trying to store an integer into a double. And normally that's fine, except I'm not storing a integer in a lowercase d double where it does the conversion automatically. If it's a capital D double, it doesn't do the conversion automatically. On an exam, on paper, I'm not actually going to care if you forget that. But in order to convert it into a double, I'll start out with 1.0 times. And then what's going on here? That should have worked. Required type string. Oh, right. It needs 2 fields. Username. Boom. All right, see, there's the error again, and now. So like I said, it's one long thing now. I could have just simply, again, I could split this up into 3 lines and like extract these individual variables. But what is average logins dot put the username and then the total time that they spent logged in, divide by the number of times they logged in. Okay. All right. So, and believe it or not, that finishes up the final exam review. So here is the important things to note for this. I know that so your final homework is due on the last day of class, but normally we do this whole demoing thing, right? Okay, so all it is just reach out to either Kenichi or to me, okay, when you're done with it, and we can schedule time over Zoom, and we'll just simply do it. And as long as we get it done by let's say the second, let's just demo, as long as we can get it demoed by like the second week, when I'll finally put in the second week of finals, when I'll finally put in final grades, we're good. Okay, now let's go ahead and just talk about where that final is, or not where the final is, but when that final is. And then I'll get to the where in a bit, okay? And I find out the when the same way you do, which is by going to the final exam schedule. Right? And I'm going to share my screen again. Share screen. And here we go. Final exam schedule. Okay, I will get the where it is. Yes, I will still take that extra credit. Okay. So we might be going, oh, okay, let's just look for our meeting time. But instead, we need to go to that last page and say, aha, all main campus day sections of 1166 and 2168 will have common final examinations Thursday, 5/2. That typically means we hold it in the same room as all the other sections, and then you have to put up with me making jokes to the other professors while you're busy trying to work and I'm being all distracting. Nah, it's not nearly that bad. But typically what we do is we hold these, it's going to be from 3:30 to 5:30 on this time, and I will email you more details later because we're just in the middle of the email thread. We've, Professor David Dobor is the person writing the exam this time, and he has done a marvelous job, in my opinion, of writing a very nice, clear, concise final exam, and one that is fair. It's utilizing a number of questions he's utilizing a number of questions I've asked in the past, and just tweaking them for semester. They're all fair. And they should be fairly straightforward for you to do. And the main, now, let me just say, in previous semesters, we've had issues with, and if you need to go, this is fine. This is just a few minor administrative things. In previous semesters, I've had students complain about the difficulty of the final, but it's not actually the difficulty of the final that we've had with students. It's the fact that the common final typically isn't 5/2, which is like the second day of finals. Typically, it's on the Thursday, it's typically on the Tuesday, 5/7, where it's the last day of finals and people are exhausted. So hopefully this should be a bit better than normal. Now, the last thing that people are concerned about would be grades, right? What is your grade? How do I get my grade? Is there a curve? Works like this. I look, when all the grades are in, I sort the grades from highest to lowest. Raw grades, I never actually adjust the points you get. It's always, this is the numeric score, right? So I sort them for highest to lowest, and I go through and I look for a break point, right? So typically what I'll see is I'll see something like a 90.1, an 89.9. And to me, there's not really too much of a difference between an 89.9 and a 90.1, right? And then I'll see a 89.7, and then I'll see an 80, and then this is just examples. Then I've seen and then I see an 88.2. Well, there wasn't much of a difference between an 90.1 and an 89.9, and there's not much difference between an 89.7 and an 89.9. But between an 89.7 and an 88.1, that's a fairly large jump there. There's not a clump like I normally find. So in that case, what I'll do is I'll draw the line in between them as far as the cutoff point. And everybody who got above a 90 will get an A. It never hurts anybody, right? Never, but what it will be is that I use the minuses to bump people up. I never use the minus to hurt a student's grade. The minus was always to bump a student up from like maybe a B plus to an A minus. Okay, so those students who got an 89 will get that. In previous semesters, the cutoff for an A minus was an 88.5. And then like the 88s, 87s got B pluses. So, but if you get above a 90 raw score, you get an A, guaranteed. Above a raw score of 80, you get a B. The lowest you can get in this class, if you actually tried and have been showing up throughout the semester, is a D. I don't give out Fs to students because a D keeps you from progressing, and that's all I care about if you don't understand the material, right? Making sure you don't go into the next class unprepared. Fs, the reason I don't do that is because I've had arguments with the financial aid office about documentation and the way I need to report things and the way they interpret what the dates I sent to them, and that affecting student FAFSA stuff. And I don't want to deal with that headache anymore because once was enough. I literally had a student who I gave an F to, and what I did is I ended up having to go to the financial aid office with her and yell at them on her behalf so that she would get her so that her financial aid wouldn't be revoked because I followed their instructions correctly. So now I just don't do that with financial aid anymore. Students the only way you get Fs is that if you just haven't tried, like haven't turned in your assignments and didn't show up to exams, that's Fs. Ds otherwise, because they effectively do what I need them to do. Okay. All right. Now so hopefully I've answered all general questions. Any specific questions, please let me know. I'm going to go ahead and stop sharing my screen, and then I will answer the specific questions and I'll stop recording.